Hey guys, welcome to this video. So it's focused on the linear dependence and Wronskian. So if you consider the set of functions given by capital F here, okay, if f1, f2 up to fn, then we say that f is linearly dependent on the interval I if alpha 1 f1 plus alpha 2 f2 plus alpha n fn is equal 0 if this only has one solution. Okay, and in this case, so for us to show that the set f is linearly independent on this interval, we have to make sure that if you multiply each function here by a coefficient, here this alpha 1 times f1, alpha 2 times f2 till after n times fn, it should be 0, that these have only one solution. And what is that solution? That solution is alpha 1 equal alpha 2 equal, and this is alpha n, this should be 0, okay? This is the solution. And this solution is on this interval. All right, let's take an example and see. Let's consider this set. F is equal x squared plus x for x 2. We want to show that this set is linearly independent, okay? So let's use these definitions. We have to find the solution to alpha times x to the power 4, x to the power 2 plus x plus beta times 4x plus gamma times 2 is equal 0, okay? So how do you solve this equation? Well, if you consider the value of x, if you say for x, when x is equal 0, what do we have? When x is equal 0, the equation is gamma times 2 is equal 0, okay? This clearly means that gamma is 0. Then if we consider x minus 1, we have minus 4 beta plus 2 gamma is equal 0. And we know that gamma is already 0. It means beta is equal 0. And lastly, if we take x, any other value, x equal 2, then this is 6 alpha is equal 0 because beta and gammas are already 0. So this means that gamma is equal 0, okay? In conclusion, we see that alpha is equal beta is equal gamma, and this is equal 0. And we conclude that f, the set f is linearly independent. All right, now let's consider the case where we have the following set. If you have set f is equal f1, f2, f3, we want to show that this set is linearly independent. By definition, if you use the definition, this is alpha 1 f1 plus alpha 2 f2 plus alpha 3 f3 is equal 0. So if you differentiate these functions, this will give alpha 1 f prime 1 plus alpha 2 f prime 2 plus alpha 3 f prime 3 is equal 0. If we differentiate again, we obtain alpha 1 f second derivative plus alpha 2 second derivative of f2 plus alpha 3 second derivative of f3, okay? So this is what we obtain, and the matrix form of this equation is the following. This is f1 prime, f second derivative of f1, f2 second derivative of f2, f3 first derivative of f3, and second derivative of f3. This multiply alpha 1, alpha 2, and alpha 3. This is equal to 0 vector. All right, let's call this guy M. If we call this the matrix M, and this is the vector alpha, then we see that M times alpha is equal to 0, okay? They are all vectors. So this is equal to 0. Then if m is invertible, then the only solution here is just alpha equals 0, okay? If M, the matrix M is invertible, it means you can divide everything here by M, and you remain with alpha equals 0, okay? So this means that alpha equals 0 is the only solution. So this clearly means that alpha 1 is equal alpha 2 is equal alpha 3, and this is equal 0. Okay, with this in mind, let me take a quick example. Let's call this one example 2. So this was example 1. We want to show that the set is linearly independent on R. So as an example, we want to consider this set and show that this set is linearly independent on R, okay? Our interval here is R. So we use this method. We want to define this M. This M is also called Wronskian. I'll explain it in what to follow. So let's consider M of omega is the first derivative. We use the same method here. The function is 1, 0, 0. The second one is x, 1, 0. And the third one is x squared, 1, 2x, and 1 and 2. Okay? So if we find the determinant of this, we obtain 2. This is different from 0. And the conclusion is that this set is linearly independent. So every time when I compute the Wronskian and it's different from 0, the conclusion is clear. It is a linearly independent set. Now, if we want to generalize this and we consider, the set of f1, f2, up to fn, all these functions f1, f2, up to fn are all smooth functions. They admit a derivative up to at least order n minus 1. So the Wronskian, by definition here, is, so the general formula of the Wronskian is therefore given by this, okay? Now, if it's happened that there exists a certain x0 in the interval, okay? So if we can find an x0, if we can find a x0 value in the interval such that the Wronskian of that value at that value is different from 0, then we conclude that the system is linearly independent. Okay? Okay, take note of this. Although the non-zero Wronskian implies that the set is linearly independent, but the linearly independent set does not imply that the Wronskian is non-zero at all points of the interval. Okay? So what I'm saying here is this can be satisfied that the system is linearly independent, but it doesn't mean that the Wronskian will be 0 at all points in the set. So as you can see here, we have chosen only 1 point. 1 point is enough to show that when the Wronskian at that point is equal 0, is different from 0, then the system is linearly independent. Okay? So similarly, a Wronskian that is 0 everywhere does not mean that the system is linearly dependent. So you must take note of this. Okay? So let's take this example and see. Let's call this example 3. So let's consider this set f is equal x squared, comma x. Okay? We want to show that this set is linearly dependent. So let's use the Wronskian and see here. This is x squared, 2x, and here is x, and this one is 2 absolute value of this. So if you cross multiply this, you see that it is 2x squared minus 2x squared, which is equal 0, okay? The Wronskian gives us 0, but we can conclude from this case that the system is linearly dependent, right? We have to check again. Let's check using this method and see. So if you call this alpha x squared plus beta x is equal 0, in this case, if the absolute value is negative, x is negative, the absolute value bring the negative, then we have alpha minus beta is equal 0. If the absolute value is positive, you have alpha plus beta is equal 0. And if you solve these two, you come to a conclusion that alpha is equal beta is equal 0, then it means that this system is linearly independent. Okay, so if you first stop at this stage when you obtain the Wronskian equals 0 and make your conclusion that the system is linearly dependent, that would be wrong. You have to check with this method, and this method now show you that the system is linearly independent. Okay, so just to sum up, when the Wronskian is different from 0, it clearly means that the system is linearly independent. But when the system is linearly independent, it doesn't mean that the Wronskian is 0 everywhere on the interval. Now, for the second point, if the Wronskians give me 0, I can conclude that the system is linearly dependent, as we can see here in this example. Okay, so I still have to check, as you can see here. When I check using the definition, I come to a conclusion that the system is linearly, this case, the system is linearly independent. So this is all for this video. I hope it is understandable. So we will be using these two methods. This is the definition, then this is the Wronskian method to show whether a set is linearly dependent or not. Okay, that is all. Thank you.